A spider's web is more than just a spider's house. This homemade glistening material has some spidey strength of its own. Spider silk is tougher than Kevlar, more flexible than nylon, and thinner than a single strand of human hair, making this super material one of the strongest materials in the world, biological or man-made. And the combination of its strength and stretch is exactly why scientists are obsessed with cloning spider silk. Now, there are 7 types of spider silks, but one has caught the eye of scientists worldwide.
It's called dragline silk, and it's the silk that they use to make the framework of the web and the radii, but they also, the reason it's called dragline is that whenever they walk, they leave the silk behind.
This is Randy Lewis, a molecular biologist at Utah State University, known for his pioneering efforts in producing synthetic spider silk. Now, Lewis and other scientists say that silk is so strong, it could be used in advances in artificial ligaments, surgical sutures, and hernia meshes. While other spider threads rely on one protein, this one combines 2. With protein structures that build and lock onto each other almost like Legos. This builds up the strand's strength and elasticity, with bonds so strong even water can't penetrate them. But you can't just take these silks from spiders. Spiders are actually notoriously bad at spinning their own threads. They'll make strands that are inconsistent in diameter, making them fine for this, but not necessarily for this. So Lewis and his team have had to turn to other methods.
In terms of the spider silk protein, we've got to find a cheap way to make it.
Randy and his team took the spider silk gene from their lab and decided to transfer it into other organisms to see if protein production could happen through other processes.
Now, we started with bacteria because they're easy, they're fast.
But researchers also tried to see if they could grow it in plants, like alfalfa, or insert the spider silk-laden bacteria into goats.
We moved the gene from our bacteria into goats, and so they produce the spider silk protein in the milk, and we collect the milk and purify the spider silk protein from that.
But the most efficient method they discovered? Silkworms. This method is still being used today, with Lewis's lab both making and spinning synthetic spider thread. The next step is actually using it.
We know that certainly has possibilities for artificial ligaments and artificial tendons, because we know that we can make material right now that's stronger than a human tendon for the same diameter.
And it's not just tendons and ligaments. Researchers have been experimenting with using spider threads to reconnect severed nerves. Traditionally, nerve repair is often limited to gaps smaller than 3 centimeters, using transplanted nerves or hollow conduits to fill the space. But spider silk can actually extend beyond that length without becoming brittle and breaking.
This makes it very, very special.
This is Christine Radke, who led a team of researchers to develop a technique using spider silk to connect damaged nerves.
We had a gap in a nerve, and in that gap we put in longitudinal direction our spider silk, and we could see nerve regeneration over that gap.
The team tested this method on sheep, since they found that sheep's nerves closely replicated those of humans, and they discovered that the nerve cells would use the spider silk almost like a trellis, growing along the thread.
And on spider silk, they go crazy. They proliferate. That's exactly what we need for repair, for regeneration. So if the extremity is moving, it doesn't rupture. And on the other side, it's flexible as well. And that's exactly what we need. So it's a perfect material, and we only could find that in nature.
And then there's the recovery period. Research has shown that human cells won't reject the spider silk, and Radke's team has found that silk can simply dissolve into the human body after doing its job.
So the spider silk will be there for a certain time, and afterwards it will be degraded by macrophages, so it will disappear.
So with all this possibility, the question is, what has been done with these silks?
Absolutely nothing.
There's still a lot of hesitation around spider silks, and the Food and Drug Administration still have yet to approve the biomaterial for use in the medical industry and beyond. Some simply see it as risky.
The next step will be that we have to do clinical studies and obviously as well financing.
Spider silk is also extremely expensive to make, so businesses would need to discover another cheaper way to make it. So all this research and then nothing?
I think the whole idea of being able to design a fiber with properties that we want it to have, rather than just taking what the spiders have given us so far, is also a big deal.
And that work is still happening. Other startups are looking to use the silk in medicinal fields, military applications, and even as biofabrics for things like bulletproof clothes. So scientists can continue to learn from cloning spider silks and designing the proteins, knowing that spider silks